This is the SI system of units. It contains 7 base units, each defined using a physical constant, and any other unit you care about can be expressed as a product of powers of these base units in exactly one way. The base quantities of the SI are time, length, mass, current, temperature, luminous intensity, and amount of substance. This makes sense because those quantities are all reasonably fundamental and we measure them a lot. However, it's not the only approach you can take. For instance, there was this joke proposal made by Jan Measley a couple of years ago, which I highly recommend you watch, where everything is derived not from time, length and mass, but from frequency, velocity and energy, the joke being that all the base units can be represented by some variation on the letter C. Slightly more seriously, there are systems of natural units, such as the Planck Units. The base quantities of the Planck Units are quite complicated to express in terms of SI, and it's not immediately obvious how you would untangle these to derive units of length, mass and time. There is a way to solve this, not just for the Planck units, but in general for systems built on any base quantities you like. But to get there, we have to think about units in a completely different way. Very often in mathematics, when we have situations involving several different changing values, we find it helpful to think of these values as the coordinates of some kind of abstract space. For example, you've probably seen this puzzle before. You have 2 jars that can hold 3 and 5 litres of water, and your job is to get exactly 4 litres of water into the larger jar. But both containers are unmarked, so there are constraints on how exactly you're allowed to move water. If you treat the amounts of water in the 2 jars as coordinates on a grid, each square represents one possible state that the system can be in, and solving the puzzle involves thinking about how you can move around this diagram within the constraints of the problem, in terms of what action each movement corresponds to. Or we could think about a pendulum. If we want to describe the state of this pendulum, the only things that matter are the angle it makes off the vertical and the speed at which that angle is changing. This means that we can represent every possible state of this system in a coordinate plane, and then consider how a point moves around this plane. For instance, we might recognise that if there's no air resistance, our point will move around an ellipse centred on the origin. This isn't a real ellipse, of course. The pendulum itself is moving in a circular arc. It's just an abstract construction that we're using to help make sense of what's going on. And with this, we come on to units. Specifically, I care about coherent systems of units, which refers to any system where we start with a handful of base units and just multiply and divide them together to derive everything else. For example, let's take a quantity that's complicated to express in terms of SI base units, like capacitance. The SI unit for capacitance is the farad, which is a shorthand for this, which really is a shorthand for this. We don't normally write out the units that have powers of 0, but it's still helpful to treat them as though they're there. In fact, to be precise about things, let's define this as a fixed format. Anytime we want to write anything in SI base units, we write them in this exact order: seconds, meters, kilograms, amps, Kelvin, candelas, moles, and we include the ones that have powers of 0. If we always do this, then the units themselves don't really convey that much information. They're just labels that always stay the same. They're defined as part of the format. So really, this is just an ordered list of 7 numbers. And then maybe we make the arbitrary decision to, instead of writing these numbers left to right, put them top to bottom. And would you look at that, we have a column vector. In other words, what we've done is define a 7-dimensional abstract vector space that contains a vector representing every possible quantity you could ever derive within the SI. Mass has a vector. Thermal conductivity has a vector. The 99th derivative of position has a vector, and each one is completely unique. So, why? Why would you want to do this? I mean, with the examples I gave earlier, those abstract spaces were useful because we were only dealing with 2 numbers, so we could easily visualise things on a plane. But you can't visualise a 7-dimensional vector space, so what exactly is this representation good for? The answer is that a lot of the mathematics behind using systems based on different units and converting between them becomes much more elegant when we can start doing linear algebra to it. So, in order for linear algebra to make any sense at all in this context, we have to start with a few basic definitions about our system. Namely, we have to define what each of the basis vectors mean. In this case, those basis vectors represent the 7 base quantities that are used in the SI, in this specific order. What this means is that, for instance, the vector with a 1 in its first entry and zeros everywhere else means time. The vector with a 1 only in its second entry means length, and so on. The next thing we need is to make sure that the basic operations of linear algebra, vector addition and scalar multiplication, are meaningful. Well, since our numbers represent exponents, vector addition looks like multiplying quantities. For instance, the mass vector plus the acceleration vector produces the force vector. Scalar multiplication, meanwhile, looks like raising something to a power, like how the area vector is 2 times the length vector because area is length squared. With those basic definitions out of the way, we can check that the axioms of linear algebra apply. These axioms are a set of 8 rules that our system must follow if we want anything we do to make any sense. I won't go through them all, but they're on the screen if you want to verify that they do apply to the situation we're working with. So, we now have everything we need to start working with this system using all the tools that linear algebra has to offer. Of course, the most important of these tools is matrices, so a natural question to ask would be, what do matrices mean here? What operation do they correspond to? Before we get to that, though, I should point something out. The basis vectors we're working with represent quantities, not units. Our first basis vector means time, not 1 second. This means that a derived quantity like velocity always looks like length divided by time, regardless of whether we're expressing it in meters per second, or miles per hour, or furlongs per fortnight. The vector for velocity is always the same in these cases because we always derive velocity from SI base units as length divided by time, and those base units define the basis vectors of our system. So, what happens if we try using a different set of basis vectors? What happens if we put in, say, the ridiculous 7c's units from earlier? Instead of time, length, mass and current, we derive things from frequency, velocity, energy and charge. This is a perfectly valid system of measurement, and we can use it to write anything that can also be written in SI. It'll look different from what we're used to, of course, but this, for instance, is a completely acceptable way to write mass, provided we've defined our basis vectors in a way that makes it acceptable. What we'd like is a good way of converting between this system and the SI system that we're familiar with. In the case of the 7c's, the base quantities are straightforward enough that you could just work out the algebra by hand without too much difficulty, but that's no fun, and we'd like a method that works for any crazy system you might want to try. This is where the matrices come in. Converting between two systems with different basis vectors is called, appropriately enough, a change of basis, and it's an operation that we can describe with a square matrix. Each row of this matrix represents one of our SI base quantities, and each column represents one of our new base quantities written in terms of SI. The first column is the SI vector for frequency, the second is the SI vector for velocity, and so on. This matrix will allow us to convert any 7c's vector into an SI vector. For instance, if we put in the mass vector from earlier, we get the vector 0010000, which does indeed represent mass in SI. Or put another way, this is stating that energy divided by velocity squared equals mass. If it's not clear why this should work, you can think of this matrix vector multiplication as writing mass in terms of the 7c's, substituting each base quantity with its SI equivalent, and then simplifying the result. And of course, there's nothing special about the 7c's here, this works for any system built on abnormal base units. This is all lovely, but converting out of a different system is the easy part. The hard part is converting into it, so we'd like to know if we can go the other way. As a matter of fact, we can, we just invert the matrix. This would be a horrible experience if we had to do it by hand, but fortunately we have computers that will happily do it for us. So let's try it out. We can plug in some SI vector, say capacitance, multiply it by our inverted conversion matrix, and we find that capacitance equals charge squared divided by energy. And you can verify that this is indeed a valid representation of capacitance. So, brilliant! We now have a tool that can take in any coherent system of units and provide a way to convert to and from SI. So far this might seem sort of useless since the 7C system is openly meant as a joke, so let's look at a slightly more practical use case. The Planck units are one of many examples of so-called natural units. They're not meant for measuring things at a human scale, rather they're designed to make the maths easier in certain areas of physics. You start by picking some number of important physical constants, and you define them all to have a value of 1 when expressed in the system. Then you derive everything else from those. This turns out to be quite useful. If, for instance, you want to describe some object moving at 1/5 the speed of light, it's a lot easier if you can just refer to its speed as 0.2. One thing you might notice is that there are 7 SI base units, but only 5 Planck base units. There are no Planck units involving luminous intensity or amount of substance, no equivalent to the candela or the mole, so we can't derive them. This isn't really a problem because they don't come up much in situations where the Planck units are helpful, but it does mean we're essentially working in a 5-dimensional space instead of a 7-dimensional one. In other words, we can only derive quantities whose SI vectors would end 0, 0, which means we might as well not bother writing the last 2 rows. Anyway, if I told you to look at this table and tell me how to derive a unit of, say, length, well, it's not clear where you would even start. Most of the units on these base quantities are not simple, and actually running through all the algebra just seems like it would be a nightmare. It's not even clear how you could get a computer to go through the process of untangling these. If we use our conversion matrix, however, everything becomes much neater. Each column of this is the SI vector representing one of our base quantities. Inverting this matrix, which is a well-defined procedure so we can get a computer to do it, produces a tool for expressing SI quantities in terms of Planck units, and it looks like this. Okay, so it's not pretty, and most of the entries are no longer integers, but all that means is that lots of our units are going to have square roots in them. This might feel like an odd concept, since it never happens using the SI, but there's nothing mathematically wrong with it. If you imagine inventing a system which included area as a base quantity, for example, then your unit of length would obviously be derived as the square root of area. This is just a more complicated version of that. Anyway, if we want to use this to find, for instance, the Planck unit of time, which is referred to imaginatively as the Planck time, we just multiply this matrix by our time vector. Actually, we don't technically need to do any calculations for this. Multiplying by any basis vector just pulls out one of the columns, so the Planck time is, by definition, represented by the first column of this matrix. The Planck length is represented by the second column, and so on. Now, if we wanted to find something more complicated, like our old friend capacitance, we can again multiply it by this conversion matrix, and we find that the units of the Planck capacitance are surprisingly nice. I don't know if there's a situation where you'd ever need to use the Planck capacitance, but you can. Now, here's the thing. This is a very effective tool, and to me at least, watching it in action feels a bit like magic. But actually putting together all these matrices and inverting them and doing the multiplication is a bit time consuming, so I've put together a spreadsheet that does it automatically. You can make a system with any base quantities you like, with units of any size you like, and the spreadsheet will do all the matrix calculation for you. It will tell you the dimensions of all of your derived units and their size in terms of SI. There's a link to this spreadsheet in the description, so you can make a copy and play around if you want. There is one more thing I want to talk about regarding unit systems as vector spaces, and it involves something I mentioned earlier called coherence. Earlier, I defined a coherence system as one where you start with some base units and just multiply and divide them to derive everything else. This definition works okay, but I'm going to change it to something slightly more specific. You might have heard people use coherence to refer to a system where you don't need to do any unit conversions. So, for instance, a system that measures length in meters and time in seconds and speed in miles per hour is not coherent, because dividing your unit of length by your unit of time does not produce your unit of speed. You have to do extra maths to get the unit you want. This is a better definition, but it's still not perfect. Consider a system that looks like this, where we're defining base units for time, length, mass, and energy. This is a problem because energy can already be derived from time, length, and mass. Or if you want to be symmetric about it, you can say that time can be derived from length, mass, and energy, or something like that. The point is that if you have 3 of these base units, you can always derive the other one. In the language of linear algebra, we would say that these basis vectors are not linearly independent. This means that energy, or indeed any unit in this system, can be represented by infinitely many different vectors, all of them equally valid. So if you're converting into this system, how do you know which one to use? The answer is, you don't. If you write out the matrix to convert this into SI, its determinant is 0. This means that you can't take an inverse, so there is no matrix to convert from SI into the time, length, mass, energy system. In other words, we can define a coherent system as one where every possible quantity either can't be expressed, or can be expressed in exactly one way by multiplying base units together. And a way to test whether a system is coherent is to take the determinant of the matrix that converts from it into SI and check whether it's equal to 0. I think this is an interesting exercise, not because it's exceptionally useful in itself, I mean, no one is ever going to use, say, the 7Cs system for anything practical, but because it demonstrates the power of thinking of one construct in terms of a different one. When we stripped away all the labels that come with a quantity in the SI, we saw it for what it was, an ordered list of numbers, and that led naturally into talking about vectors and vector spaces, which opened up the whole world of linear algebra and all the valuable tools that come with it. If you've been conditioned to think of vectors as nothing more than arrows in space, it might seem like a strange step to take. But vectors, like a lot of things in maths, are not fixed with one meaning. They are whatever they need to be useful for the problem at hand. So yes, out of context, saying that mass is a vector is nonsensical. Nothing is a vector, but vectors can represent anything we like, so long as we find it helpful.